Hello, everyone. Thank you for joining us. And sorry for getting started a little late. We had some technical issues that we had to sort out. My name is Judy. I am very excited to welcome you back this month for the Journal Club on a very interesting topic. And first of all, for those people who have texted me and emailed and asked why we didn't have one last month, we had a scheduling conflict and we couldn't make it. And so it was a last minute travel change for the presenter. And instead of doing a rush job, we decided to just move on to the next month. This evening, we are very, very honored to have two amazing panelists and Samuel, who's an MD, PhD student at Harvard, and a good friend of mine, Andrew Beam. And well, I'm not going to try and describe what he does. I think it's amazing work, and he's going to get an opportunity to introduce himself and share his passion. And so the paper that we're discussing today is this paper that they wrote on adversarial attacks on medical AI, and why this is a health policy challenge. And I will sort of have an opportunity to also ask the panelists questions in the later part of our webinar, but this paper, could not have been more timely given what was happening with the Israeli group that we linked this to one of the, the descriptions for this webinar, and these researchers ended up introducing some errors just by bringing a USB into the reading room. I think this is a really interesting area for us to understand, and I'm even more excited to know that not only technical solutions are required, but broader solutions, and I hope you can be a part of this. So without further delay, I'm going to pass on the baton to Sam, and look forward to an exciting webinar, and thank you for joining.
Wonderful. Okay, let's see. Let's make sure. Can you guys see my screen okay? Let's see how we're doing here. Okay.
Judy, correct me if I'm wrong, but only the panelists can speak, so audience members cannot ask questions during and or give feedback. Is that correct?
Take that as a yes.
Yes, the audience can see the slides, and they have a place that they start sending questions, and I unfortunately have to become their voice and ask the questions on their behalf, because it's not very interactive, and it's just a go-to-meeting webinar restriction.
One more question. Given that this is an AI journal club, can we assume that people have heard the words machine learning and or deep learning before?
Yes.
Okay, great.
Okay, wonderful. So I'll go ahead and start off here. And I think before we really jump into the meat of the paper, what we sort of wanted to do, we thought, was provide a bit more more global context for this work, sort of where it fits into sort of a taxonomy of potential pitfalls in medical machine learning. And in order to do this, I'm going to sort of present a variation on some slides that I recently presented at an ophthalmology conference, which I think will hopefully be helpful in sort of situating this work in sort of a broader context. And if at any point this gets boring and you guys want to flag, just skip this stuff, get to the meat of the paper, we can do that as well. So feel free to ping Judy if that's the preference. But in any event, so let's see how this works. Ooh, okay, wonderful. So not going to dwell on this. This is sort of the obligatory deep learning and machine learning are awesome slide. But on the left here is sort of a canonical at this point image, which shows the sort of progress over time on the ImageNet challenge, which is sort of this famous competition in computer vision, and it was sort of for a number of years it was considered this incredibly challenging task to have computers be able to look at an image and tell which of 1,000 categories that image came from. And what's nice about this slide, and the reason it's so popular, is because you can sort of see in a single data point when the sort of deep learning revolution was on. And that was in 2012 with AlexNet, which I don't know if you guys can see my cursor okay, but basically you can see that there was like a very fundamental step function drop in error rates when this deep learning phenomenon really emerged and was incredibly successful. And ever since, this has sort of been driving this rapid progress in machine learning with those same techniques adapted to an array of different problems. And in medicine, this has been sort of the first low-hanging fruits of machine learning in healthcare have been likewise in these imaging challenges, and adapting basically these same techniques that have been really popular since about 2012, although they have a long history going back decades before that. And we're very pro AI. We think that the excitement around machine learning in medicine is warranted. And in particular, I'm really excited after meeting some of these guys to see and follow the success of this IDX software system, hopefully, which is sort of the first FDA approval for a fully autonomous diagnostic algorithm and imaging system that is literally being operated right now by people with only high school educations and being treated fully and legally with malpractice insurance like it's a doctor giving diagnoses. So that's actually happening right now, which is pretty darn cool. So,
or pretty darn scary depending on who you are.
Yeah, depending on who you are. I think they've done a pretty good job. But I think for all the excitement, it's important to sort of stress that the clinical benefit of AI is pretty hypothetical at this stage still. There have been very few prospective trials of medical AI reported in any specialty. As of January, I think it was only 4 pretty much ever. And a lot of these models have been struggling to reproduce their findings in new patient populations. And a sort of a canonical example of that, I think, is this CC Cruiser paper, which came out recently, where they had one small prospective trial, and they had an incredible performance. It was 98.8% accuracy, which was better than the physicians involved. And then they deployed it in a new setting with a much larger trial, and the performance dropped all the way down to 87%, whereas the physicians stayed up at 99%. And I think that's sort of a nice depiction in one sort of case study of both the opportunity and the challenge, because we can have systems that perform really well, but we haven't quite figured out how to get them all the way to delivering benefit. And on that note, there's never still been a trial that actually tries to show clinical outcomes being improved by ML. So that's still a long-standing challenge. But my claim, and we'll hopefully get into these pitfalls right away here, is that it's really the effective integration and teamwork between the clinical experts and the machine learning experts that's going to drive the sort of final mile or set of miles in this transition from sort of promise to impact. And I think that this is sort of an important point to stress, and because one of the things that sort of shifted with deep learning is that we don't need experts in the same way that we used to. And what I mean by that is it used to be the case that clinical experts were really important for helping engineer features or take inputs and decide precisely what needs to go into the algorithm. But with deep learning, a lot of the awesomeness of deep learning is that it can learn, in many cases, these features by itself from scratch on raw data. So in a lot of ways, there's sort of a challenge being issued in that we don't need clinical experts the way we used to. But what I'm going to sort of argue briefly is that we still need them a lot, and that they're going to be really important here. In order to do that, I'm going to sort of quickly review the machine learning development pipeline as it's traditionally existed. And this usually, it starts with you define an important question and you go gather a bunch of retrospective data. You split that into training data and labels and test data and labels. And then you look at that data and see how it's formulated, and you use that to design a model. And then once you've designed that model, you're going to train it on the training data, validate it on the test data, and then hopefully that works and is showing promise. And at that point, you can integrate it into the clinic and deploy it, and then test it on prospective data, at which point we're going to have the opportunity to sort of really inform decision making and ultimately have sort of model impact. And what I'm going to sort of introduce this paper as part of is one of these taxonomies of questions that we need clinical experts to be asking in this pipeline. And to sort of motivate this, I'm going to briefly talk about some of the other key questions along these different stages, and it will sort of culminate with the adversarial examples, and then I'll switch it over to Andy to talk from there. So the first sort of set of questions happens at this data curation stage. And the hypothetical example that I'm using to motivate this question, which is, how might our model be tainted with information from the future? And so the example I'm giving is, you have this, you want to train your machine learning algorithm to detect a pneumothorax, and you guys are all famous physicians at this point, so you guys can hire postdocs, unlike me who has to do all this grunt work myself. And you have your postdoc download all the x-rays in your database and uses the diagnoses at discharge to gather cases and controls. And then you train that information. So with the strong hint at the top, I bet at this point a lot of you have figured out what could go wrong here. And the answer is that there's a chest tube in the image, and what the model may actually be learning to do is diagnose the treatment instead of the disease. And that's called label leakage, and it's a really common problem. The next sort of question is, okay, so you have a postdoc, he's going to do it again, he's going to make sure he limits the images to before the treatment has, or before any diagnosis or treatment has been made. And then he takes all those images and splits them up randomly into the training and the test set. And then you have these two images. This is the first image in the training set, this is the first image in the test set. What could go wrong here? Well, so these are different images, but they're actually from the same patient. And that's the sort of phenomenon we call trained test set leakage. And that's really dangerous too, because what we ultimately want to do with a test set is sort of simulate how well this algorithm might be doing on unseen data. And if you're training it and testing it on data from the same patients, that's really risky, because what you're going to do is you're going to overestimate the model accuracy on unseen patients, and that's called trained test set leakage. And again, both of these things are sort of process, data gathering process issues that I think clinicians have a really important role in detecting and sort of catching. And you guys, as parts of these projects, especially if you're collaborating with ML people, you need to have your eyes out really sharp for these types of issues. But the real place that you need those eyes to be super sharp, I think, is when it comes to confounding. And we're very familiar with confounding in statistical models, but I think that in sort of classic epidemiology type studies, but confounding in machine learning can often be really, really pernicious. So here's a hypothetical example for this, which is, have a machine learning classifier, you want to detect hip fractures, you gather some patients, or a bunch of images from your database. Some of them happen to have come from an ED, and some of them from an outpatient clinic, and some of them from a different inpatient clinic. And you don't really pay attention to the site of the origin of the images, or what time they were coming from, or any of that type of stuff. And the question is sort of, how could that process screw you over? And obviously the answer is confounding, but I think that a lot of people don't really appreciate how huge of a problem this can be. So to demonstrate this, this is data from a patient that I have the reference for down here on the side. Joel Dudley was, I think, the senior author on it. And what they did is they took a pretty darn good classifier, not amazing by modern standards, but pretty darn good for hip fractures, I think it was. Oh, this is a residual thing, sorry. And if you take that classifier and you apply it on a nicely, the data was split such that the patient, there wasn't any patients across the training and the test set, and they didn't have any treatment or hardware in the images and stuff. So all the previous issues we've talked about so far were kosher. But it turned out that an algorithm that had an AUC of like 0.85 turned out that if you matched the patients on simple non-imaging features before you passed into the algorithm, the AUC dropped down to below 0.7. And if you then match additionally on healthcare process variables, things that shouldn't have anything to do with a hip fracture, like what time of day the image was acquired, what scanner model was going on, the image was taken on, the performance dropped to completely random. And basically what's happening here is deep learning models are really perceptive, but they're not principled in the sense that they don't know what they're supposed to be looking for, and they can find any sort of local optimum that will help them solve the problem. And it turns out, as that will surprise none of you, if you have a patient that's able to stand up and walk to a standing scanner, he's going to have a very different prior of having a big bad fracture than one that can't get out of bed and has to have the portable scanner brought to him. And you have a very different prior of a patient who's in the emergency department at 4 a.m. versus somebody that's was able to wait till the next morning and walk into an outpatient clinic at 12 in the afternoon. And I think, one of our colleagues and good friends, Rajman Rai, did a study with lab values to talk about a different type of data. And they showed that for a bunch of variables, the time of the day that the lab value was ordered had actually a stronger predictive performance than the value itself of the lab.
You're getting the wrong Zach postdoc credit for that paper. I think that was Dennis's paper.
You know what? I think you're right. I think it was actually Griffin. We're both wrong.
Dennis did one with Griffin and Zach, but yeah, someone in Zach's lab.
Yeah. Anyway, I think it was Griffin and Dennis and Zach. You're right. Sorry. Thank you. Nice catch. Good fact check. So that's a super important problem. So the next one, and I promise there aren't 3 for every one of these. So the next one's sort of be at model evaluation. So here's another hypothetical example. You guys have, a great paper, but then reviewer number 2, gosh darn him, says, okay, I need to see your performance stratified by race. And you find big differences. So you go, okay, well, no harm done. We're just going to gather some more data from the minority population on which the model was performing the worst, and we'll fix it right up. But then it turns out that the performance doesn't improve, or all the performance goes up a little bit, but the disparity doesn't go away. And the sort of question is, what could be going on? And the answer comes from this really great paper at NeurIPS this last year from Irene Chen. And what she showed is that there isn't sort of such a single concept called discrimination or bias, that there's actually different types of discriminatory bias that can be arising in different machine learning settings. And the nature of the bias, they sort of break it down into sort of this bias variance noise trade-off, if you guys are familiar with statistics. And they show that in different settings, you might need to solve a racial bias or other sorts of discrimination by gathering more data. In different situations, you might have to gather more features. In different situations, you might have to try different models on different populations. And so we need to be sort of acutely aware of the fact that performance isn't sort of a defined entity, and even that bias itself isn't a single finite entity, and that we need to sort of involve the statisticians and really check out what's going on here, so that we can make sure that these models are fair, and when they are not fair, that we really pay attention to that and give it the attention it deserves, not just assume that it's going to go away with bigger scale or something. So now the last one is going to come out with model deployment. And the hypothetical example here is going to be, okay, so you guys deploy your system at a hospital, and it works really, really great in this orange curve for a couple years. And then all of a sudden, we have a sudden drop in performance. Everyone's freaking out. And you talk to the IT team and say, okay, you guys clearly have done something wrong here. What happened? And they say, hey, the model is exactly the same. We just ran all our tests on the same training set, and everything works just fine. And this is, again, real retrospective data. And in this case, it was that there was a new HR system installed. And they installed Epic, and everything broke. And the reason it broke was because again, these models depend very specifically on the little input variables, and it happened to be the case that when they switched to a new coding system, even though they were pulling out all the same, ICD codes and stuff, it turned out that the new system, prompted the doctors to create their data in a slightly different way. And the real lesson here is that there's this concept called dataset shift, which means that performance isn't a fixed entity either, because the data that we feed our models can change over time. And we have to be really vigilant about this. And again, just like it's the clinicians that are going to have the insights into the potential confounders and the potential biases and are going to be the ones that are vetting this, we need clinicians to be paying vigilant attention to this and be able to ask the question, okay, not just like in this last slide, is the population that I'm hoping to use this model on the same as the population that it was trained on? But also, even if the population is fundamentally the same, has the data that I'm feeding it changed with respect to the data that it was trained on? And if there's any possibility that it is, you need to be vigilant about validating it and having an ongoing process of making sure that our models are working and updating them as necessary. And sort of that brings us to this model impact. And the question that I want to ask with model impact is sort of, are there potential unintended consequences of our deployment? And the first of those, and there's many beyond this, you know, are the disparities of access, are there, you know, all these other issues, but the two I wanted to highlight, and this will lead me over to Andy. The first one is that diagnosis is not outcomes. And again, this is obvious when we say it, but it's not always obvious when we are working with these systems and building them and feeling really good about ourselves. But I think our friends from oncology can attest to the fact that, you know, thyroid cancer, for one example, our ability to diagnose it has gone through the roof, but the impact on treatment has been essentially nothing because mortality has been flat. And there are other cases where you know, there's a real cost and a real danger associated with a diagnosis that may or may not be actionable. And we need to sort of be humble and keep in mind that diagnosis isn't outcomes, and that we need to know how to use the models, when to use the models, how to interpret the outputs, and to avoid a sort of overdiagnosis problem. And this is something that, you know, again, calls for, you know, a real definition of meaningful clinical outcomes of any system that we want to develop, and making sure that we're tracking and testing those over time, not just sort of performance on some benchmark data set. And then the last question that will queue up Andy is there a potential mismatch in incentives between the person that's creating the algorithm and the person that's sending data into that algorithm? And, you know, why on earth would that be something that we need to worry about? And that is the cue for Andy.
All right, so if you could pass me the ball, I'll take it. All right. So can everyone see my slides?
I can.
Okay, so Sam, if you see it, that's enough. We can go with that. So thanks to Sam for that wonderful broad overview of sort of all the ways machine learning can go. So I don't know what previous journal clubs have been like, but I hope that they have gotten you excited and hopeful about the potential for AI in medicine. We're going to be a little bit of a wet blanket tonight, but just to be clear, not to put words in Sam's mouth, but I think I know where he stands on this. We're extremely excited about AI in medicine. We're extremely hopeful that it's going to improve access to care, hopefully maybe wrangle costs under control, and just make healthcare work better. But what we're talking about tonight are things that we need to be thinking about as AI in healthcare becomes more widely deployed. What Sam just gave was a wonderful overview of all the things that we should be thinking about. What I'm going to transition to talk about now is a very specific, a very provocative, a very startling way in which medical AI can break down. It can actually be manipulated, and we'll talk about how that works. And then we'll sort of outline the reasons why someone might want to manipulate a medical AI system, all the different ways that this could happen, and then maybe try to conclude on a more positive note about maybe ways we can mitigate this and a possible path forward. All right, so given that we've seen this radical progress in medical AI, as I think as radiologists, you all probably acutely feel this, that medical imaging has sort of been at the forefront of progress in medical AI. What are some ways that this can go wrong? So what I'm going to be talking about here is actually the message is spread across two different papers. One paper was published last month. It's sort of a high-level policy piece. And then there's a technical piece of this paper that describes the nitty-gritty details. Warning to my MD friends on the call, it has some calculus in it. That content is in a preprint that's available online that you can also go and read. But I'm going to be pulling from both of these papers, so if you'd like to refer back to any of this material later, it will be in one of these two papers that I'm showing here. All right, so just to reiterate, medical imaging specifically has seen amazing progress through the use of these deep neural nets, through the use of deep learning. It's likely that other parts of medicine may follow suit, but certainly I think it's without question that medical imaging is undergoing a revolution from the application of deep learning models to medical imaging, be it x-rays, be it fundus photographs of the retina, dermatology images. Sort of, if you can take a picture of it, there's a deep neural net that can provide some type of diagnostic decision support. So this is the sort of provocative question, especially given that most of the folks on this call are radiologists. Given this sort of burst in capabilities from machine learning and deep learning in medical imaging, should we seriously consider automating some, most, any of medical imaging tasks? If there's a computer that can do it faster, cheaper, better, should we seriously entertain, at least in the short term, handing over those responsibilities to an algorithm? If we did that, what could possibly go wrong? What are some unintended consequences of doing that? Like I said, Sam touched on some sort of obvious, well, maybe not obvious, some subtle problems of doing that. But these are sort of problems that it's hard to attribute to malfeasance or to ill intent. But what we're going to talk about now is if someone really wants to manipulate a system, could they do that to a deep learning system? And so the thing that I think sort of gets lost in the parade of progress from deep learning is that we tend to anthropomorphize things that do a task, quote unquote, as well as a human. But it turns out that these deep learning algorithms are extremely brittle, that they are very easy to break, especially if you're trying to break them. And what we're going to go over now is if there's a malicious actor, they can actually exert arbitrary control over a deep learning system using something called an adversarial attack. So this is the only mathy slide in the talk, I promise. You don't need to know exactly how a neural net works. All you need to know is that they're defined, they learn from data through the use of partial derivatives. If you don't remember back to your undergrad calculus classes, just remember that partial derivative tells you how something changes when you change it a little bit. So if we want to know how the neural net's probability of having a pneumothorax versus no pneumothorax and a chest x-ray, as we sort of twiddle the pixels, the partial derivatives are going to tell us that input-output mapping. So what, is this just nerd stuff? Does anyone actually care about this? Well, it turns out that we can use this knowledge of calculus and how the neural net works to make an extremely small change to the input that maximally changes the output. And so what's really surprising is just how small the change in the input is, can be to generate an enormous change in the output. So this is what we're going to call an adversarial attack. Just to be concrete, when we say the words adversarial attack, it's going to be a modification to an input to a machine learning algorithm that is designed to change the output of that algorithm. So you can think about, if you have a chest x-ray, what pixels do I need to change in order to get the neural net to provide the diagnosis that I want it to provide? And then so the next slide, we're gonna go through a very concrete example of constructing an adversarial attack, and then we're gonna ruminate on whether this is a problem for medical deep learning systems. So this is one of the examples from the preprint and from the paper. Sam, actually, I was going to say we, but actually this is all credit to Sam, built 3 deep learning classifiers that represent the state of the art in the field. So these are classifiers for dermatology, for radiology, and for ophthalmology. What I'm about to show you here is the dermatology classifier. So I'm showing you here a benign mole. We take this image, We present it to our dermatology deep learning classifier and ask its opinion. The deep learning classifier correctly provides with near 100% confidence that this is a benign mole, no need to worry. And this is when the adversarial magic happens. So what we do next, using calculus that I mentioned on the previous slide, is we construct, and again, when I say we, I mean Sam, construct something called adversarial noise. So to you and me, this patch that I'm showing on the screen sort of looks like snow fuzz from an old TV, if you remember that. I don't know how old you guys are, but I remember that. It looks like snow on a TV. We're going to take this fuzz and add it to the image to create a new image. So this image to human eyes looks exactly the same. You can get up close, you can zoom in on this picture, and at the resolution that human eyes can see, you're not going to be able to tell a difference between this image, which I'm calling an adversarial example, to the original image on the left of the slide. So while this image does not look different to humans, to our neural nets, these two images look as different as night and day. So recall on the left when we showed the original image to the neural nets, it's 100% confident it's benign. However, when we show this new example, which again looks the same to us, it's now 100% confident that this is a malignant lesion that probably needs action. And so this is the crux of what we mean when we say an adversarial attack. So there's a couple things worth pointing out at this point. One, this sort of demonstrates the fact that neural nets are brittle, that their visual systems do not work the same way that human visual systems work. It points out that they're actually easy to fool or manipulate. So if you have some working knowledge of calculus and access to a reasonable computer, you too could fool a neural net to have it give you whatever diagnosis you would like it to. So this is just a summary of the results from all three imaging modalities, so from ophthalmology to radiology to dermatology, from left to right. What we're showing in each patch is the top row of each image in the top row is a normal, i.e. non-diseased image. Each image in the bottom row has some type of disease. The confidence, the percentage number that you're seeing in the bottom left-hand corner of each image tells you the neural net's confidence as to whether or not that image contains a disease, an instance of the disease class. And then the columns going from left to right are the original and then the adversarial examples. So what this is telling you at a high level is that we can manipulate these neural nets to provide whatever diagnosis we want. In this case, we wanted to just have them be wrong. We wanted to have them always give the wrong answer. If we wanted to instead have them always say that there's a disease present, whether or not there actually is a disease present, we can do that too. And of course, we could do the opposite and say there's no disease in any of these images. But this is just showing that we can manipulate these systems across all these different medical imaging modalities. And again, these classifiers are more or less representative of the state of the art. So this isn't a function of these classifiers just aren't as accurate as things that have been published. The ability to attack a system is completely independent from how accurate that system is. All right, so those are the sort of nuts and bolts of what an adversarial attack on a medical deep learning system is. The question that Sam and I get asked the most is this just sort of computer science trivia? Is there any reason that we should actually worry about these things being operationalized within an actual healthcare environment? And so I'm going to ask you to imagine a hypothetical future which actually resembles the present day more and more, in which there are clinically validated deep learning systems that have been thoughtfully designed by clinicians in light of all of the pitfalls that Sam highlighted earlier. So there's no confounding. These things generalize perfectly. There's accurate as physicians. And we have gotten all the technical validation right. And now these things sort of serve as the gold standard for diagnostic capability in medical imaging. So even in this hypothetical future, what could someone do with one of these adversarial examples? So I'm happy that this isn't a journal club for dermatologists because I'm about to pick on them a little bit. But imagine that I'm a private practice dermatologist. I'm operating under some fee-for-service model. I would like to increase the number of biopsies my practice does by 10% or so. And so if there's a lesion that is on the borderline of being malignant, but this gold standard deep learning classifier that has been so well validated doesn't think it's malignant, I'm going to put my thumb on the scale a little bit and, using an adversarial example, add just enough to push that lesion over the edge and then allow me to do my biopsy. So likewise, you could imagine a shady pharma company who's running a trial where tumor burden is one of the primary or secondary endpoints that's assessed using chest x-rays that's evaluated by one of these deep learning gold standard algorithms. And again, I could put my thumb on the trial to essentially ensure a positive result from that trial, regardless of whether or not my drug actually works. And so the thing to be, and we go into sort of a much broader spectrum of possible attacks in the policy paper. And if you find this kind of, this line of thinking provocative or intriguing, definitely encourage you to go read that paper. But the thing to keep in mind is that the healthcare economy, especially in the US, is enormous. Trillions of dollars move through the healthcare economy every year. Things that make decisions about diagnosis, about treatment, therefore control billions of dollars every year. And if something is controlling that much money, there will exist in the ecosystem something that tries to manipulate that decision maker. And so in the future, we believe machine learning algorithms will be responsible for more and more decisions, and therefore may be subject or targets for manipulation. And adversarial examples would be one way in which you might manipulate machine learning algorithms in the healthcare economy. Another thing just to point out, like I said, radiology especially has been at the vanguard of progress in medical AI, but these types of attacks are not restricted to just medical imaging. You can do adversarial text substitutions. So if you're submitting a written patient report and a deep learning algorithm is reading that report and deciding whether or not someone's at risk for opioids, for example, you could figure out the set of substitutions that would make, that are English synonyms, but would nonetheless make the deep learning algorithm more likely to say that this patient's at low risk for opioid abuse. Likewise, if this is really easy to imagine in the context of insurance, billing, and reimbursement, if you're submitting a bunch of billing codes for your patient, and on the other side of that transaction is a deep learning algorithm that looks at all the codes and decides whether or not to approve or deny that claim, you could have an adversarial attack that would give you the maximum set of, the set of codes that's most likely to result in an approved claim, but are still mostly synonyms for the actual set of symptoms that the patient had. Once we get to the end, I'll let Sam, yeah, go ahead. I knew that you wanted to add some color there. I was about to set you up.
Oh, just, yeah, oh, sorry, yeah, just two very small comments on this. So one of them, that adversarial coding example, that's a real example. And what I mean by that is, there's a paper that's referenced, that number 13 there, actually, if you pull up the paper, that we found a real article from the Endocrine Society, I think it was, that was basically saying, hey, we've noticed that if you bill for metabolic syndrome in the setting of obesity, it doesn't get approved. So don't use metabolic syndrome, use the other codes that are related to it, but just make sure you don't include that code if you want to be able to bill for your patients. And it was an altruistic motivation. But what we are saying here is that, like, basically this is something that's ongoing now. Adversarial attacks don't just work on deep learning algorithms, they work on sort of all sorts of machine learning algorithms. And in a lot of ways, this is an extension of this sort of like ad war online that is happening between advertising agencies and people that are trying to get their websites showing up, and spammers, and people that are trying to make email protectors. And what we sort of anticipate is the extension of this sort of same phenomenon into this sort of upcoding war that we already have going on today. Sorry, that was too much talk.
No, that's perfect. And I was pausing there because I felt sure that that's a part where you want to jump in. And so what Sam was saying there is that one thing in that subtext is there could actually be altruistic reasons to do this. So for organ donation or organ transplantation, if you think that if a doctor has their best patient at heart, or best intentions at heart, they could try to do something like this. And adversarial examples, to Sam's point, already exist between, in this case, humans trying to find the set of codes that the insurance agent on the other side that is most likely to reimburse. Machine learning offers an opportunity to sort of make this systematic and at a much larger scale, because you can do these targeted adversarial attacks, and you know that if a machine learning algorithm is doing it, that there's an opportunity to do that. And so just to reiterate something that Sam said, there's a company called IDX that has one of these machines that is FDA approved. Sam was at ARVO last weekend and learned a lot about it. And one of the things he mentioned is that you just have to be a high school technician. You can operate it, or high school level education with some amount of training after that, and you're allowed to operate this, provide a diagnosis without the oversight of a physician. So this is a clear example of an algorithm essentially making the diagnosis on its own. So just to sum up, and I'd be happy to hear if there have been any questions throughout the talk, but again, just to reiterate, we think deep learning, machine learning, more generally, data-driven decision science in medicine is a good thing. We're certainly not saying we should stop doing research in medical AI, medical machine learning, or even just better forms of epidemiology to make decision making. But we are saying that a lot of these things have very subtle drawbacks that we don't feel are appreciated by the mainstream sort of medical community, and we're trying to draw attention to that. And just, this is another question that we almost always get. There are no known defenses. There are no known defenses for adversarial attacks in the general case. So if you have a black box machine learning algorithm that you cannot make any assumptions about, and there are no known defenses of how to stop someone from performing an adversarial attack against that machine learning algorithm. There are domain-specific adaptations, but again, in the general case, there's no defense. Putting all that together, adversarial attacks could be an implementation to clinical use and adoption of deep learning systems. And again, if a deep learning, if an AI system or if a computer system is making a healthcare decision, then it's going to control the flow of money and therefore be a target. So I think this brings up a very interesting balance, or a very interesting trade-off that we should be thinking about. So if we were taking adversarial examples seriously, how do we balance the competing objectives of fast and accurate diagnosis for a patient versus sort of protecting the healthcare system as a whole? So you could protect the healthcare system as a whole by sort of reducing the accuracy of these systems, which would increase their robustness to an adversarial attack. But then individual patients are going to pay the price for this through either false positives, false negatives, and just sort of a deterioration of their healthcare services. Again, just to reiterate, we're super excited about AI. We just want to get out in front of these sort of pernicious, bringing it back to Sam's presentation, pernicious data, confounding, validation, bias issues, and in this specific case, the potential for bad actors in the healthcare system to abuse machine learning systems through the use of adversarial attacks. So I think that's all that's all we have for everyone tonight. We'd be happy to now take some questions, or Sam and I'm sure could fill 10 to 15 minutes just bantering about anything. So.
Awesome, guys, this is fantastic. I mean, I had high expectations, but this is like, wow, So yeah, to the attendees, please, if you would like to put some questions in the question box, and I can pass them on to Sam and Andrew. One thing that they both did not do is tell us who they are, and I didn't do that because I assumed that they would. Yeah. So do you want to take a few minutes to do that?
Sure. Sam, you go first.
Okay. Yeah, so I'm an MD PhD student working with Zach Kohane. here at Harvard Medical School. So basically, you guys, I'm sure, are all very familiar with the MD PhD pipeline. I'm just in the sort of hopefully the second to last year of the PhD phase and doing a bunch of projects in machine learning for healthcare. One of which was this, but I'm actually sort of transitioning a lot more into like drug development and diagnosis of rare disease using big neural nets and such.
Cool. So I'm Andy Beam. I currently wear a few hats. So my day job is I'm head of machine learning at a startup here in Boston, where we use deep learning, the exact same stuff we've been talking about today, to help improve the way that we engineer proteins. So we have neural nets that actually design primary sequences of amino acids that do the thing that we want them to do. In addition to that, I serve as something called Senior Fellow at Flagship Pioneering. So Flagship is a venture firm here in Boston. They're the one who started the startup where I work. I help advise them across some of their portfolio companies about where the application of machine learning, deep learning AI may be helpful. I try to help them think through. They're traditionally just a sort of a bio firm, so not even really biotech. Biotech's probably fair, but they're sort of a bio-first company. They have lots of hardcore biologists, and they are sort of trying to think about how AI may help them solve some really interesting problems in biology, and I'm trying to help them think through that process. In July of this year, I will be coming back to academia and starting my own group at the Harvard School of Public Health in the Department of Epidemiology, where I will be getting back to more traditional AI and healthcare types of problems with a special focus on the neonatal intensive care unit.
Okay, awesome, thanks. So I have two questions for you, Varun. Thanks for attending. And Varun asks, not to ask for anything overly prescriptive, but what would your general policy ideas be, perhaps for protecting against adversarial attacks?
Go for it, Andy.
I was gonna say go for it, Sam. Yeah. So there's some pretty simple healthcare IT solutions that come to mind immediately. So essentially, as soon as an image is created, you can create something called a hash, which is like a fingerprint for that image. And so you could store this hash like cheaply and easily in the healthcare environment, and then you would know if anyone had modified the image. So if you do one of these adversarial attacks, you're modifying the pixels, and if you created a new fingerprint, then you'd be able to compare that to the original, and you could see if it had changed. Problem with that solution, as I'm sure you guys know, is that healthcare IT is hard to update, it's slow, it's expensive, and sort of any sort of infrastructure change like that is pretty difficult. All right, so Sam, I did one, you do another.
Oh yeah, so another one that actually, funnily enough, this sort of shows where our biases are. We spent so much time thinking about these technical and sort of big policy solutions. I think a lot of MDs that I've talked to have pointed out that another natural place to advocate for is thinking about cutting off the incentives for these at the source. So like, how can we do a better job aligning the incentives of the providers with the payers? You know, and thinking about
like,
the problems.
That's more like, how do you fix the U.S. healthcare system as a whole? That seems even harder than just updating the infrastructure.
Yeah, I'm sure that's true. But I think the billing problem, for example, is going to be really hard to eliminate without doing something like that. You know, there's other sort of technical things we could talk about as well. Like you could add a second neural network whose job is just to try to detect adversarial examples or not, which in some cases is shown to be useful. And then any given model, like depending on the data that it's getting into, you could do sort of clever tricks that are sort of variants of what Andy talked about with hashing the images. But it's tricky.
It's tricky. So I think the fundamental insight here is one that cybersecurity has known for a long time, is that it's easier to break things than it is to fix them. And so I don't think Sam and I know what the bulletproof solution is for this, because to be honest, it doesn't exist. But we are hoping that at least by starting the dialogue that we can encourage fellow ML researchers to take this problem seriously to help us come up with solutions.
Awesome. Teresa has a question. Thanks for attending. Thank you for the great presentations. My name is Teresa. I'm a radiology resident at Penn. There's a lot of enthusiasm for generative adversarial networks in the setting of generating CT images from MR data and for use with rare diseases by slightly altering data to increase case numbers. What are your thoughts on these applications?
I have opinions, but I want to hear Andy's first.
Well, so there is some confusion that's due to precisely one person. That the word adversarial appears in at least 2 different contexts. So what we're talking about here are adversarial attacks. I believe what the questioner is asking is about generative adversarial networks, aka GANs. So both of these things were invented by the same guy named Ian Goodfellow. And they're doing different things. So a GAN is able to hallucinate realistic looking data or realistic looking fake data that has the same statistical properties as real data. I think, Sam,
go ahead.
But I think the heart of your question is, can you use this to get more data for free? And statistically, you can't. That there's going to be parts of the real probability data distribution that just because the GAN is hallucinating new data, it's not going to be able to generate from. So it's only going to generate data from the parts of the data distribution that it has seen. So it's no substitute for having more real data, but it could perhaps buy you a few percentage improvement points in whatever metric you're measuring. So I'll stop rambling there and then pass the ball back to Sam.
Yeah, I think that, so GANs, I've called GANs the refined sugar of machine learning research because they're really, really fun. But I think we still have sort of a lot to prove in terms of making sure they actually work as advertised. If any of you want to see how cool they are, you could Google after this, like, I think this person is not real or something. This person does not exist. I think maybe one of those, there's a website called that, and it's just the website, every time you update it, it shows you another fake image of a person that does not exist, but you would be very hard pressed to know that if you didn't know ahead of time that it might not be real.
Yeah, I'm showing this on the screen now. So yeah, if you're still tuned into the screen here, this person does not exist. This person was hallucinated by a GAN. It is not a real person.
Yeah, it's just crazy. The problem though, and the cool thing with GANs that is still unproven is, I think, there's a specific example being asked, which is, can you use these networks that can clearly generate really beautiful images to change data into other forms? So like you could use sort of tweaks on something like a GAN, often something called like a UNet or something like that, that people have tried to use to turn MRIs into CTs and vice versa, or have tried to take histopathology slides and generate them as if they were generated using a different stain. And the sort of question, I think, was sort of, do we buy that? And I am a little bit hesitant to endorse that. I think it's a really cool idea, but I'm always a little bit nervous because, again, the data is still fundamentally synthetic, and I think that it really comes down to, if the signal that you want to see is in the original image, it's just easier to see in another format, then I think we got a good shot. But if the problem is that the thing you're looking for isn't visible in a CT scan, but you're hoping that by turning it into an MRI, you're going to be able to see something that wasn't in the original data, I'm going to be really skeptical that you're going to be able to do that, because if the data isn't in the original sample, it's not going to suddenly be created. Something will be created that will seem plausible, but it will just be made up in like an average of the distribution that it's coming from. So I'm hoping for really good testing before any of those algorithms get anywhere near a hospital. But if they tested it and it worked, then I'll be pumped, because I think it's really cool.
One interesting, I was going to talk about Brett's paper. One interesting application that one of our friends and colleagues, Brett Bolu-Jones, did as part of his PhD is did a GAN, but coupled it with what's called a differential privacy mechanism, where the goal is not to hallucinate new data. it was to generate a synthetic set of EHR data that retained the statistical properties of the original data, but you were not able to successfully re-identify people in the original data. So I think that's an interesting application where you can use a GAN to create new data that has some set of desirable properties, in this case privacy, that would allow you to share otherwise sort of HIPAA data, PHI data.
And I personally think the lowest hanging fruit for GANs, because I'm a little nervous with Brett's thing. I think it's awesome again. And I definitely trust the differential privacy part. What I'm nervous about is whether or not it's going to be useful for downstream data mining in the same way the original data was. I think that remains to be proven, but I really hope it works. I think the easiest low-hanging fruit for GANs in healthcare might be in education, actually, because all you need to do is generate something.
That's just because you wrote a paper on that.
Well, I wrote it because I thought that it was the thing, and I'm not the only person that said that, it turns out. But yeah, it's a good rib. It's a good rib. But I think that's a setting where we don't have to worry as much about privacy, and we don't have to worry so much if it's like perfect. We just sort of need it to be something that can be helpful to a person training their eye, needing a few more examples. And I think that might be one use case in the shorter term that might be easy for it.
Awesome. Well, we are past 6, so I'm going to sort of ask the last question, which is, what are you excited about the next 6 months? You know, it's getting close. Okay, I guess it's not 6 months, it's 8 months, but getting close towards the mid of the year. And what are you excited about the future, the immediate future, or a project that you're working on, and just something to share with the participants?
Well, I'm excited to meet Andy's baby, which she's been working on.
I'm training a neural net as we speak, but it won't be ready until July. So.
Yeah. Andy will have a radiology baby, but yes, so he wouldn't replace us. But okay. And Andy, are you excited about being a dad?
I'm excited is one of the emotions that I'm feeling for sure. But on the science front, the protein world has really opened my eyes about so many applications that we can use deep learning, AI, and medicine for therapeutic development. So I think that there's a ton of what essentially is low-hanging fruit there. On the sort of broader, like longer time lines, I am really excited about moving beyond just deep learning. To be clear, I'm going to try to write a bunch of deep learning papers over the next year. But I think that having deep learning be a component of a medical decision making that is cognizant and aware of all some of the issues that Sam pointed out. There's a lot of interesting methodological challenges to get us there. Causal inference is one of the big buzzwords right now, having a model that has a richer model of the world and can understand, at least at some level, cause and effect to make intelligent medical decisions. So I think that inching us closer towards things that are not just statistical pattern recognizers, but actually have what we would recognize as some level of intelligence is what I'm excited about.
Yeah, and along the same theme, my sort of serious scientific answer is I'm getting a little bit excited about the idea of marrying neural networks with sort of big knowledge bases, because this is sort of like the first wave of AI was about reasoning over sort of expert curated sets of facts and using logic, and that didn't really work that well. But what we're sort of exploring now is sort of a way to combine sort of the spirit of that original approach, which was bringing in expert knowledge and then using neural networks to learn to reason over that knowledge and sort of make sort of fuzzy connections across them, and using that as a way to sort of hopefully help the neural network act smarter in areas when it hasn't seen data before. And the area that I'm trying to apply that to is in diagnosis of ultra rare disease patients through this thing we call the Undiagnosed Disease Network here at Harvard, where it's a bunch of, it's sort of, if you couldn't design a harder task for a neural network as they're currently designed, because every patient in this database is basically one of a kind. Which makes it really, really hard for humans and really, really hard for neural networks. So we're trying to figure out ways to have the neural networks use expert knowledge to sort of maybe hopefully be able to give diagnoses to some of these patients that teams of doctors haven't been able to yet.
Awesome. Thank you so much for your time this evening. Thank you to the attendees. Thank you, Catherine, who really stays late to staff this for us. We appreciate your help, and this was a fantastic talk. You know, most of our talks, people will go back and you know, watch through them. This has been great, and especially Sam, your slides. I was kind of envious when you posted them on you know, like the slides from your talk, but to hear you describe you know, sort of like adversarial attacks and sort of this new area of bias and new thoughts about medicine is just great. You both really made this topic very consumable, even for less technical listeners. So thank you very much.
Thank you so much.
Yeah.
Thanks, Judy. This was fun.
Okay. Thanks, guys, and see you next month. And hopefully some of you will be at ACR. And yeah, thanks.
Bye.